Jai Hind, ladies and gentlemen. A very warm welcome to each one of you. Aviation Safety India takes great pleasure in presenting a video presentation on recovery from upset conditions. During last couple of videos, we had discussed factors which can lead to upset conditions. This video presentation will mainly discuss the recovery techniques from different upset conditions. So let's move on to the video presentation. During this video presentation, we shall be covering objective of UPRT training, what is airplane upset, what is stall, recovery technique from stall, nose high, wings level, nose low, wings level, high bank angle, nose high, recovery technique, high bank angle, nose low, before concluding the presentation. First, we shall have a look at the objective of upset recovery training. The objective of upset recovery training are to increase the pilot's ability to recognize and avoid upset situations, and to improve the pilot's ability to recover control if avoidance is not successful. What is aeroplane upset? Just to refresh your memory, an aeroplane in flight unintentionally exceeding the parameters normally experienced in line operations or training and defined by the existence of at least one of the following parameters: pitch attitude greater than 25 degrees, nose up; pitch attitude greater than 10 degrees, nose down; bank angle greater than 45 degrees. Within the above parameters, but flying at air speeds inappropriate for the conditions. Now we shall discuss what is stall. All of you are aware of what is stall. Just to refresh your memory, an airplane is stalled when the angle of attack is beyond the stalling angle. A stall is characterized by any of or a combination of the following: buffeting, which could be heavy at times; a lack of pitch authority; a lack of roll control; inability to arrest descent rate. Now, these characteristics are usually accompanied by a continuous stall warning. Pilots must remember that an airplane wing can be stalled at any airspeed and any altitude. Moreover, attitude has no relationship to the aerodynamic stall. Even if the airplane is in descent with what appears like ample airspeed, the wing surface can be stalled. If the angle of attack is greater than the stall angle, the surface will stall. Most pilots are experienced in the simulator or even airplane exercises that involve an approach to the stall. This is a dramatically different condition than recovery from an actual stall because the technique is not the same. The present approach to stall technique being taught for testing is focused on powering out of the near stalled condition with an emphasis on minimum loss of altitude. At high altitude, this technique may be totally inadequate due to the lack of excess thrust. It is impossible to recover from a stalled condition without reducing the angle of attack, and that will certainly result in a loss of altitude regardless of how close the aeroplane is to the ground. Although the thrust vector may supplement the recovery, it is not the primary control. At stall angles of attack, the drag is very high and thrust available may be marginal. Also, if the engines are at idle, the acceleration could be very slow, thus extending the recovery. At high altitudes, where the available thrust is reduced, it is even less of a benefit to the pilot. The elevator is the primary control to recover from a stalled condition because without reducing the angle of attack, the airplane will remain in a stalled condition until ground impact, regardless of the altitude at which it started. Weather effects that could cause a slowdown or stall at high altitudes. At high altitudes, the upper air current, such as the jet stream, becomes significant. Velocities in the jet stream can be very high and can present a beneficial tailwind or a troublesome headwind. Wind shear at the boundaries of the jet stream can cause severe turbulence and unexpected changes in airspeed or Mach number. This wind shear or other disturbances can cause substantial and immediate airspeed decreases in cruise as well as in climb situations. If the airplane is performance limited due to high altitude and subsequently encounters an area of decreasing velocity due to wind shear, in severe cases, the backside of the power curve may be encountered. The pilot will have to either increase thrust or decrease angle of attack to allow the airspeed to build back to normal climb of the cruise speeds. This may require trading altitude for airspeed to accelerate out of the backside of the power curve region if additional thrust is not available. Now we shall discuss recovery technique from a stall. A stall must not be confused with a stall warning that occurs before the stall and warns of an approaching stall. Recovery from an approach to stall warning is not the same as recovering from a stall. An approach to stall is a controlled flight maneuver, but a stall is an out of control condition, but it is recoverable. If the airplane is stalled, it is necessary to first recover from the stalled condition before initiating upset recovery techniques. Effective stall recovery requires a deliberate and smooth reduction in wing angle of attack. The elevator is the primary pitch control in all flight conditions and not thrust. Although stall angle of attack is normally constant for a given configuration, At high altitude, swept wing turbojet airplanes may stall at a reduced angle of attack due to Mach effects. The pitch attitude will also be significantly lower at high altitude than what is experienced at lower altitudes. Low speed buffet will likely precede an impending stall. Thrust available to supplement the recovery will be dramatically reduced, and the pitch control through the elevator must be used. The goal of minimizing altitude loss must be secondary to recovering from the stall. Pilots must exchange altitude for airspeed. Only after positive stall recovery has been achieved can altitude recovery be prioritized. Now we shall talk about recovery techniques, nose high, wings level. Let's look at the situation. Pitch attitude unintentionally more than 25-degree nose high and increasing. Airspeed decreasing rapidly. Ability to maneuver decreasing. In this situation, the pilots must start by disengaging the autopilot and auto throttle and recognize and confirm the situation. Next, pilots need to apply nose down elevator to achieve a nose down pitch rate, which may require as much as full nose down input. If a sustained column force is required to obtain the desired response, consider trimming off some of the control force. However, it may be difficult to know how much trim should be used. Therefore, care must be taken to avoid using too much trim. Pilots should not fly the airplane using pitch trim and stop trimming nose down as the required elevator force lessens. If at this point the pitch rate is not immediately under control, there are several additional techniques that may be tried. The use of the techniques depends on the circumstances of the situation and the airplane control characteristics. Pitch may be controlled by rolling the airplane to a bank angle that starts the nose down. The angle of bank should not normally exceed approximately 60 degrees. Continuous nose down elevator pressure will keep the wing angle of attack as low as possible, which will make the normal roll control effective. With airspeed as low as the onset of the stick shaker or lower, up to full deflection of the ailerons and spoilers can be used. The rolling maneuver changes the pitch rate into a turning maneuver, allowing the pitch to decrease. In most situations, these techniques should be enough to recover the airplane from the nose high wing level upset. However, other techniques may also be used to achieve a nose down pitch rate. Fly at extremely low air speeds. This reduces the upward pitch moment. In fact, in some situations, for some airplane models, it may be necessary to reduce thrust to prevent the angle of attack from continuing to increase. This usually results in the nose lowering at high speeds and a milder pitch down. This makes it easier to recover to level flight. If control provided by the ailerons and spoilers is ineffective, rudder input may be required to induce a rolling maneuver for recovery. Only a small amount of rudder input is needed. Too much rudder applied too quickly or held too long may result in loss of lateral and directional control. Hence, caution must be used when applying rudder because of the low energy situation. To complete the recovery, roll to wings level. If necessary, as the nose approaches the horizon, recover to slightly nose low attitude to reduce the potential for entering another upset. Check airspeed and adjust thrust and pitch as required. Nose high wing level recovery. To summarize, recognize and confirm the situation, disengage autopilot and auto throttle, apply as much as full nose down elevator, use appropriate techniques. Roll to obtain a nose down pitch rate, reduced thrust underwing mounted engines. Complete the recovery, approaching horizon, roll to wings level, check airspeed, adjust thrust and establish pitch attitude. Now we shall discuss recovery techniques, nose low, wings level. The situation, the pitch attitude unintentionally more than 10-degree nose low, airspeed low. Pilots must recognize and confirm the situation. They should disengage the autopilot and auto throttle. Even in a nose low, low speed situation, the airplane may be stalled at a relatively low pitch. Hence, it is necessary to recover from the stall first. This may require nose down elevator, which may not be intuitive. Once recovered from the stall, then pilots can apply the thrust. The nose must be returned to the desired pitch by applying nose up elevator. Pilots must avoid a secondary stall as indicated by stall warning or airplane buffet. Airplane limitations of G-forces and airspeed must be respected. Now we shall discuss recovery techniques nose low, wings level, but airspeed is high. Situation, pitch attitude unintentionally more than 10-degree, nose low and airspeed high. Recovery technique, recognize and confirm the situation, disengage the autopilot and auto throttle, apply nose up elevator. Then it may be necessary to cautiously apply stabilizer trim to assist in obtaining the desired nose up pitch rate. Stabilizer trim may be necessary for extreme out of trim conditions. Then reduce thrust and, if required, extend speed brakes. Obviously, it is necessary to avoid impact with the terrain. So pilots should not enter into an accelerated stall by exceeding the stall angle of attack. Airplane limitations of G forces and airspeed should also be respected. Now we shall discuss recovery technique, high bank angle and nose high. Bank angles can exceed 90 degrees. In high bank situations, the primary objective is to roll the airplane in the shortest direction to near wings level. However, if the airplane is stalled, it is first necessary to recover from the stall. Situation: bank angle greater than 45 degree, pitch attitude greater than 25 degree, nose high, airspeed decreasing. A nose high angle of bank attitude requires deliberate flight control inputs. A large bank angle is useful in reducing excessively high pitch attitudes. Pilots must recognize and confirm the situation. They should disengage the autopilot and auto throttle. They should reduce the angle of attack and adjust the bank angle not to exceed 60 degree to achieve a nose down pitch rate. Maintain awareness of energy management and airplane roll rate. To complete the recovery, roll to wings level as the nose approaches the horizon. Recover to a slightly nose low attitude. Check airspeed and adjust thrust and pitch as necessary. Now we shall discuss recovery technique, high bank angle but nose low. So in this situation we have bank angle greater than 45 degree, pitch attitude lower than 10 degree, nose low, airspeed increasing. A nose low high angle of bank attitude requires prompt action because altitude is rapidly being exchanged for airspeed. Even if the airplane is at an altitude where ground impact is not an immediate concern, airspeed can rapidly increase beyond airplane design limits. Situation: bank angle greater than 45 degree, pitch attitude lower than 10 degree, nose low, airspeed increasing. Pilots must recognize and confirm the situation. They should disengage the autopilot and auto throttle. Simultaneously, application of roll and adjustment of thrust may be necessary. It may be necessary to upload the airplane by decreasing back pressure to improve roll effectiveness. It is important that positive G-force not be increased or that nose-up elevator or stabilizer trim be used until the airplane approaches wings level. If the application of full lateral control, that is ailerons and spoilers, is not satisfactory, it may be necessary to apply rudder in the direction of the desired roll. Only a small amount of rudder input is needed. Too much rudder applied too quickly or held too long may result in loss of lateral and directional control and cause structural damage. As the wings approach level, extend speed brakes if required. Ladies and gentlemen, in conclusion, please remember that aircraft oblique helicopter upset conditions have resulted in a number of serious accidents. Pilots must be knowledgeable and aware of various upset conditions and take timely and appropriate action to recover from upset conditions. It is essential for both the pilot to be situationally aware at all times, and they should have coordinated responses to any upset conditions. The knowledge and awareness of the upset conditions will prevent panic reaction and help the pilots in taking informed decisions to stay safe. Thanks a ton for your kind attention and valuable time to watch this video presentation. I'm sure that you must have found this video presentation useful, and now you'll be better informed to avoid or recover from upset conditions. Wishing you all a very happy flying and many happy landings. Jai Hind.